It's my pleasure to introduce to you today Professor Ignacio Sepulveda. Ignacio is in the Civil Construction and Environmental Engineering department at San Diego State University. He was the first hire for us in the area of coastal engineering. Being in San Diego with such an important location, it took us all this time to finally hire somebody that I think we really hired well. So his expertise is in coastal engineering, ocean modeling, uncertainty quantification, and many more things. He comes with his formal doctoral training from Cornell, followed by a postdoc at Scripps, and now he's been at San Diego State for 3 years. Right. So far. And so it was a post COVID edition, but he's off to a good start so far and does some very interesting work, and hope you find his today talk to us about what he does and possibly have opportunities for some of you to join us.
And we are looking for people. Thank you, Sachi. So thank you everyone for coming. This is kind of new topic in quotes in San Diego State. Still, we were having people working in coastal engineering in the past, probably not as a coastal engineer, but certainly there were people interested on the coast, and there are other faculties working on this. I'm not the only one doing coastal studies. So before I start with the topic of the tsunamis and all what I will show you today about tsunami science and tsunami research, I can tell you briefly what is going on with coastal engineering. Coastal engineering is a field that it was motivated or prompted by the fact that every time you are trying to build something at the coast, the coastal environment and the offshore environment is pretty complicated. If you are a civil engineer and you took the courses of hydraulics, for example, you learn a lot about Bernoulli equation. However, the problem with the Bernoulli equation is that it relies on a set of simplifications that actually are not valid in the coastal environment. Because of that, you need to learn other formulas, other models in order to understand how you can try to build something next to the coast. For example, if you want to analyze forces of wind waves, you need to understand other type of problems, okay? And that is what we have been trying to do in our group. So in the 60s and the 50s, 1950, 1960, people identified this problem and the coastal engineering field started to develop, okay? And for example, here very close to San Diego State, people at the Scripps was started with the first studies talking about what happened with wind waves, what happened with the geomorphology, how the sun moved. And all of those understandings were finally used in order to establish new formulas and new standards in order to design infrastructure next to the coast. After the 80s, after the 90s, I would say, because in the 80s it still was pretty strong. In the 90s, people started to get bored about coastal engineering. Why? Because basically we already had the formulas, we already knew somehow how to design, and therefore we could keep going with our civil engineering students, and probably some of them could skip the coastal engineering course, and everybody was fine, because the formula were in the standards. However, we arrived to 2010, 2000, and we start to identify that we have climate change. What happened? All the hazards related with the coastal environment started to change again. So now we knew, we have some knowledge, but now we need to update everything. And now, if you can see, from 2 years ago, many schools started to develop again the coastal engineering program. Why? Because we are in trouble. And if you can see, I'm not the only one who was hired a couple of years ago to start the coastal engineering, but you can see in other university people started to again inject resources to the coastal engineering field. Okay, one of the topics in the coastal engineering which caught my attention since I was very child is tsunamis. And in this presentation, I will show you the advancements which we have done in terms of tsunami science. So I'm coming from a city in southern Chile, which is called Valdivia. And Valdivia, latitude 32 south, is very famous because it was in front of the area where the largest earthquake ever recorded took place. That was the earthquake of 1960. Anyone knows what was the magnitude of that earthquake? It has been the largest, 9.5. Can you imagine a magnitude 9.5 of an earthquake? Last night at 11:42, we had a little tremor in El Centro, which was magnitude 5. Magnitude 5. Yeah. Did you feel it last night? No? I'm not surprised because it was a magnitude 5. But if you have a magnitude 6, for sure you will get scared. Right? Well, imagine that in Chile we live with magnitude 7, magnitude 8, and people keep going with the practicing. Okay? So that is Chile, and because of that, the main reason why I study these kind of tsunamis and even earthquakes and coastal hazards in general is because I'm coming from a city which was severely struck by tsunamis in the past. So I grew up watching these kind of problems. Actually, I didn't born in 1960. I was not even a project, but I knew from the traces from that earthquake that the event was huge, was a high scale, something like crossing any dimension that you can imagine in terms of geophysical processes. It was impressive. And because of that, I started my career. First of all, before academia, I had a consulting company in which we were doing tsunami hazard assessment. And you can be surprised that actually here I'm in the middle of the mountains studying tsunamis. Why? Because there was an energy company who wanted to build a dam, and there was the risk that in that dam, after an earthquake, they could have landslides from the mountains, and those landslides were prone to create tsunamis in the projected dam. And that is one of the assessments we were doing. And of course, I was working in the vast majority of the projects, working in tsunami hazard assessment in critical infrastructure. For example, that is a natural gas port in Chile, which is one of the 2 important natural gas ports in the country. Okay, so first question, why we should bother to study tsunamis? When you wake up during the morning, are you worried about tsunamis? You ever think about a tsunami? No, why not? Because the recurrence of those tsunamis are pretty low. We are talking about phenomena that are happening after several centuries, even thousands of years. So probably you don't even care about what happened with tsunami. So, for example, just using a Poisson distribution, and you think that your average lifetime is 79 years, and you want to think or you want to calculate what is actually the chance to be hit by an event that happened 1,000 years, you will realize that actually the probability in your lifetime to be hit by an event with a recurrence of 1,000 years is actually 7.6%. That is the probability that you will see an event which happened with a recurrence of every 1,000 years. That percentage of 7.6% sounds important to you? Is it small? Is large? Do you have any notion if that is important or not? Pretty big. Oregon is very big. Do you think it's very low? It's very difficult to say, right? And if you start to compare to other things that you are scared, probably that event or that percentage will be important. For example, are you scared to be diagnosed by a certain illness? Probably yes. Probably those illnesses have a probability close to 9-8%. So when you start to compare with other things that you really are afraid, and everybody is afraid, including me, you start to see that those percentages actually are not so low. Okay? Second is the fact that if this thing happens, the damage is huge. For example, here I can show you a picture of a town in an island, in an oceanic island in Chile, which is Juan Fernandez. That picture is before a tsunami, before the tsunami of 2010, and this picture is exactly at the same spot after the tsunami. You can see that a tsunami destroyed everything. And one of the most important signatures of a tsunami is the degree of economic losses that they create, that they cause, even more than a simple earthquake. Simple because they are very complex. But tsunamis can be very, very harmful. Okay? For example, the UN did a study a couple of years ago. Actually, that study came out in 2018, I think. And they say that in the last 20 years, starting from 2018, 10% of the total economic losses related with natural hazards were just related to tsunamis. Why? Because we had the tsunami of 2004 in Sumatra and the tsunami of 2011 in Japan. And all the economic losses just with those two events were given a 10% of the total economic losses of any natural hazard you can imagine in the world. So because of that reason, we really need to study tsunamis, okay? Because they are low recurrent, but actually that low recurrence is not so small. And second, if you have the bad luck to have a tsunami, the economic loss and the life losses will be huge. So you really need to have some awareness about tsunamis. Okay, so how we study tsunamis? Yeah.
Pacific versus Atlantic.
Pacific is way more recurrent to have an earthquake which can generate a tsunami. The Atlantic has some possibilities to create some tsunami-genic earthquakes. The recurrence of those subduction zones are much smaller compared to what you can have in the Pacific Rim. But it still is not negligible, and people are working on them. And even more, in the Atlantic, you can have other sources of tsunami, not necessarily earthquake, which is something we will talk later. Okay, so as any problem that you have at the coast, and every problem in which you need to try to solve an issue in coastal engineering, you need to focus on 3 dimensions. Those dimensions are, first of all, you need to collect a lot of measurements and records, and you need to be very good doing data analysis and signal processing, and also you need to have strong knowledge in physics to understand what you are measuring. Second, you need to try to provide tools to do modeling. The scales and the phenomena happening at the coast and offshore are so big that certainly at some point you just need to rely on computers and build numerical models in order to reproduce what you are observing from the nature, to try to make those bridge between source and consequence. Okay, and for that you can use a numerical model or even a physical model. People have been doing physical models, which allow us to learn many processes. And as a third dimension, also, we need to understand the uncertainties. Always our data is imperfect. We haven't measured everything. And because of that, we don't know, we don't have a perfect knowledge about how is the coastal and the marine environment. Because of that, we need to try to come up with some estimates of the uncertainties of our estimates. For example, the maximum height of a tsunami will be uncertain because we don't even know when a tsunami-genic earthquake will happen. We don't even know what will be the intensity of that earthquake, you see? So we need to, there is no way to skip the dimension of uncertainty. We need to understand the uncertainty of our estimate. And finally, once we have these 3 elements with a certain development, we can come up with some studies which can allow us to understand what is the level of hazard related with tsunami. For example, some people in the 90s were working with the most credible scenario, which was basically just select an earthquake or select any tsunami-genic source, model that tsunami-genic source and see the consequences at the coast, for example, the inundation. However, the sources are very, very uncertain, and that is how we started to jump into another perspective, which is what we call the probabilistic tsunami hazard assessment, in which now we will give the probability in a certain period of time to have a tsunami with a certain intensity or exceeding a certain intensity. Okay? And then, as another evolution, we started to think about what is actually the probability to have a structure failing because of that hazard. And that is how we jump into the fragility curves, which will give you the probability that your certain building, for example, next to the coast, will survive a certain period of year in which you are exposed to tsunamis or other coastal hazards. And after you have those quantification, you can establish some responses. For example, you will try to create a seawall in order to get protected from tsunami. But after the 2011, we discovered that actually that is not a good idea, probably because the wall will fail and finally your city will get inundated anyway. You're going to start to change the exposure of the people. For example, remove houses which are next to the coast. And finally, which is the most effective one, educate people, and every time you have a big earthquake, ask the people to try to evacuate and go to higher, or try to go to the tallest, to the highest stories or floors in a building. Okay? So what is the most effective one? In my personal opinion, education is everything. More than trying to change infrastructure, if you have a very well-educated people, you will be fine. And I can see it in Chile. That was the most effective plan in order to reduce the life losses. Okay, so in this yearbooks, there are two new elements which has been part of the advancement of the research we are doing here in the group, which is first of all study what happened with non-conventional sources of tsunamis. For example, what happened with landslide tsunamis, what happened with volcanic tsunami, which is something we will talk later. And also, we need to understand how these tsunamis interact with other coastal processes. For example, what happened with the tide. It's very different when you have a tsunami happening in a high tide compared with a tsunami of the same magnitude arriving with a low tide, for sure, right? Which will be worse? The one with the high tide, right? So that is a very important source of uncertainty. And also something that we started to work a few years ago, the sea level rise. Sea levels are going up, and that is helping tsunami to reach higher land. So it's a problem, you see? So we need to try to find the mathematical formulations in order to include both elements. Okay, so today we will talk about compounding processes, which is framing this new methodology, which we call non-stationary probabilistic tsunami hazard assessment. And then we will jump into volcanic tsunami, which is related with non-conventional sources of tsunami. So, okay, so as a brief explanation, every time you have a tsunami, let's imagine that we are considering a project lifetime. Let's imagine that we want to live in our coastal environment for 100 years. Let's imagine that T, that capital T in black, is a lifetime. It's the number of years you want to live next to the coast. For example, if you are designing a nuclear plant, that will be the number of years in which your nuclear plant will operate. 30 years, 50 years. Okay? Okay, let's imagine that the 50 years pass, and we could identify that 6 tsunamis happened during our lifetime. Let's be very pessimistic. 3 tsunamis happen in that place. Okay, here you can see a diagram showing the 3 tsunami events, and the way that little blue thing that I draw there are basically 6 tsunamis which are coming with different intensities. And those tsunamis will come with different intensities because, for example, the earthquake that created that tsunami will have a different magnitude because the depth of that earthquake was more deeper or more shallower, which also changed the intensity of the tsunami. And therefore, what you will see is actually the tsunami will come in different sizes. A tsunami will never come with the same size. Okay? They vary. Okay, but in addition to that, you have 2 problems. First of all, in every of these 6, in each of these 6 scenarios, you will have a different tide phase. Sometimes your tide will be close to the high tide. In other times, the tsunami will happen exactly when you have the low tide. Sometimes the tsunami will happen in the middle, when you are in the mean sea level. The problem is that you don't even know at what time the tsunami will arrive. And therefore, you don't have any clue what will be the state of the tide at that time. So therefore, it's an uncertainty. Even more, the tsunamis are happening in different years. And we know that the sea level is rising. Or well, in the majority of the places is rising, because there are some places in which the relative sea level actually is going down. But that is another discussion. But let's imagine that we are in California and the sea level is rising. What happened? The sea level, the market by this red line, is changing in time. And here the sea level will be, the mean sea level will be bigger or larger, higher than the mean sea level that you have, for example, today. Because the sea level is rising. And if you see, here you have the 6 tsunamis arriving to the coast, but here you can see that in every time, you will see the sea level, which is rising, but also with these blue lines, you can see what is the state of the tide in every of these 6 tsunamis. Sometimes you have low tide, sometimes you have high tide, and in addition to that, you have the sea level rise. What happened? You have a compounding process in which your tsunami is affected or exacerbated by other effects, or at least changing. Okay, because sometimes you can be super good luck and you will have a low tide, for example, and that is perfect. That will help you. You see, because the tsunami will reach lower land. Right? That makes sense? Actually, by the way, that happened in 2010 for the tsunami in Chile. They had the minimum low tide of the year, or close to that, which was very cool. But the problem is that the tsunami took many hours, and at the end, during the morning, it was inundating everything anyway, because the tide is start to rise at some point. But that is one of the reasons why the tsunami was very low in the middle of the night, because the earthquake happened in the middle of the night. But because the low tide was so low, the tsunami was not inundating anything. So we were very lucky, somehow. Bad luck, because we had the earthquake, but it was in low tide. Okay, so in order to study tsunamis, or try to evaluate the tsunami hazard, the best tool we can have is the probabilistic tsunami hazard assessment. And when we are dealing with probabilistic tsunami hazard assessment, basically we assume that our earthquakes are happening with a certain recurrence rate, which is fixed. And we are adopting a binomial distribution or a Poisson process model in order to evaluate the probability that a certain tsunami arrives in a certain exposure time capital, which is the formula you can see here. So this formula will tell you actually what is the probability of not having a tsunami which arrives with a certain recurrence rate alpha sub I. Okay, the problem is that, for example, let's imagine that that lambda is related with a certain earthquake. For example, the recurrence rate of earthquake magnitude 9. The problem is that 2 earthquakes of magnitude 9 not necessarily will create a tsunami with the same size. Why? Because those probably, or maybe those 2 earthquakes with a magnitude 9 probably will locate at different depths in the crust. Probably the dislocation pattern will be different. Probably they will be located more inland than in the ocean. And because of that, the tsunami will be different. Okay? So, in order to include that uncertainty related with the characteristic of the earthquake, you can grab the Poisson model, which is this one, and you can include a penalty term, which is that conditional probability P sub I, which is basically saying the probability distribution, the conditional probability distribution in which the tsunami height, for example, exceeds a certain critical value HC, given that you have an earthquake PI. Okay? In that distribution, you can add all the uncertainties related with the tsunami response. Okay? While the lambda sub I will tell you what is the recurrence of this source. For example, the earthquake recurrence rate that we can estimate somehow using Gutenberg Richter laws and another geophysical laws that we have in hand. Okay, so that is the probability that an earthquake and a tsunami exceeding certain value doesn't happen. And of course, 1 minus this relation will tell you what is the likelihood of having one or more tsunamis with intensity exceeding HC. And that is the classic probabilistic tsunami hazard assessment based on a Poisson model. Okay, so what would with this formula? We have a problem. And the problem is that the sea level is changing. If the sea level is changing, probabilities are changing. What is worse, having a tsunami today or having a tsunami in 100 years more? Let's imagine that the tsunami is the same. In 100 years more, you will have a sea level rise of 1 meter, let's imagine. When do you want to have your tsunami? Today or in 100 years more?
100 years.
Well, let's imagine that we will live 100 years. Well, if you have it later, it's worse. Because the sea level will be higher, and therefore the damage will be higher. Yep.
Well, wouldn't the earthquake be more deep? So you would
No, but let's imagine that the tsunami and the earthquake are the same.
Well, but the force coming out has more distance to go up.
No, but when I'm talking about earthquake depth, I'm talking about the depth with respect to the seafloor.
But still, the top is like higher, no?
No, but it's
Okay.
just related with the seafloor and the crust, not with the layer of the ocean. By the way, it's negligible compared to the depth we are talking about earthquakes. We are talking about difference of 10 kilometers, 5 kilometers, while sea level rise is 1 meter. But anyway, those are not related. One is the depth with respect to the crust, to the seafloor. Okay? A good question. Okay, so certainly this equation is not working because we have a problem that the tsunamis are getting worse with time. And that means that this little value P, which is a conditional probability given that an earthquake happens, what is the probability that a tsunami exceeds a certain intensity, this P sub I will change in time because you have sea level. And that P, the probability to exceed a 1 meter elevation probably will be higher in the future, right? Because the sea level is helping the tsunami to reach higher level. And therefore, we need to go back to the fundamentals and change and replace that formula. And for this, we are going back to the fundamentals of the derivation of the Poisson distribution. And actually, when you are working or comparing a differential of time, you can see that the binomial distribution, which is given by this formula, is exactly the same as the formulation of the Poisson process. And also when the lambda is sufficiently small by the way. Okay, if you think that in every delta t you have independent processes, what you can do is basically do a multiplication of this term that you can see here. And finally, that product of exponential can be the same or is equivalent to say that you have an exponential with an integral in the exponent, which is basically a summation in the exponent. That is an integral, right? A summation of delta t's. Okay, so having that equation or that equality, you can finally derive the new formula, which is what I call the non-stationary probabilistic tsunami hazard assessment, in which now instead of only having lambda and pi, now you have an integral of this integral. And now your conditional probability can change in time. Because you have it inside an integral in time. So you can do whatever you want with that pi. Now it can change in time. Okay? Okay. But super good, we have a formula, but the big question is how you can get values, first of all, for that probability distribution dependent on time, and second, how you will calculate that integral. Okay? And the half, or the second half of the challenge to change the formula was to try to find a numerical method to try to come up with quantities for that integral. And actually, I came up with a very simple idea. Basically, we are using collocation points and a surrogate. So let's imagine that we are calculating the value of P sub I, which we can calculate with a Monte Carlo simulation or any other more sophisticated method. In my case, I'm using a stochastic reduced order model. And let's imagine that you are building the distribution, Pi, for a certain value in which the sea level is equal to 0. Then grab your model again and set a sea level equal, for example, to 0.5 meters. And you build the distribution again. And then you do it for another fixed value of sea level, for example, 1.1 meters. Okay? So you will build those PI. And it's very simple, and you can use very standard procedure to build those PI, if you know the uncertainties. Now, if you want to know what is the value of Pi for any value of time, what you can do is a kind of surrogate model in which basically you are doing an interpolation between different times. You see how I'm achieving that? Basically just doing a linear interpolation between the different collocation points. Super simple. That is what I call, in a fancy way, a surrogate model, but it's just an interpolation between collocation. You see? So, using this idea, now you can get Pi for different times, and now you can solve the integral because you have the function for any time. What is the simplest thing you can do to solve an integral? What is the first thing you use in the first mathematics course dealing with integrals? Simpson, a quadrature, right? In which you are discretizing the integral. You can use that. And you can get an estimate of the integral that you need in a very simple way. Okay, so next question, what do we do with the tides? With the tides, we can do something similar, because if we get measurements of the tides in any location, we can get the distribution, and by getting the distribution, we can put the function of the distribution, and again, we can use the collocation points in order to include the tides inside the same function. And you can include the tides using exactly the same collocation points that you pick. And by doing that, you will have a formula, non-stationary probabilistic tsunami factor assessment, which will contain the sea level rise and will contain the tides. And you have everything. So, as very briefly here, I explain about the example. Here we were doing a probabilistic tsunami hazard assessment in the South China Sea due to earthquakes happening in the Manila subduction zone. For this work, we had to understand the uncertainty of the earthquakes. To understand the uncertainty of the earthquakes, I had to identify what was one of the most dominant sources of uncertainty of the earthquake characteristic, and that is what we call the slit distribution, which is the amount of dislocation between tectonic plates. In order to do this, I had to build a random field model. Okay? That was part of my PhD work. And using those samples of earthquakes and building the values of Pi for a stationary problem without sea level rise and without tides, we could obtain the values of probabilities to exceed a certain maximum tsunami surface elevation in Hong Kong and Kaohsiung, which are two important ports close to the Manila Trench. Now, what we also did was to apply our new formula and compare the classic probabilistic tsunami hazard assessment, which are the segmented black line, and we compare it with what happened when, three cases, when you only have tides included, which is the blue one, when you include sea level rise, which is the black continuous line, and when you include tides and sea level rise to the tsunami. So, looking at those figures, do you think it's important to add sea level rise and tides? For some values of maximum elevation, certainly yes. For example, if you are dealing with a tsunami height of this value, look at the difference. It's huge. You see? And actually, this is the reason why in California we are trying to investigate what happened with the effect of sea level rise, because it seems to be important. Let me skip that figure. Okay, so what happened in California? With Andrew Mosqueda, which is a student who was working with me last year, we started to run simulations in California. This is the port of Long Beach, okay? And in these colors, in this plot, I'm showing to you what is the tsunami elevation, which is exceeded with a probability of 2% in 50 years. That is what a stakeholder called the most credible or maximum considered tsunami. The maximum value exceeded with a probability of 2% in 50 years. So the first one is the classic PTHA, the classic probabilistic tsunami hazard assessment without sea level rise and tides, and you can see that it has values of 0.4. But then you go and do the analysis with a non-stationary probabilistic tsunami hazard assessment with tide and sea level rise, and you can see that you are doubling. You have double of the values. So that is showing to you that actually you need to reconsider how we are building our hazard. Because if we have sea level rise, we will increase the hazard. You see? And actually here we have some distribution. This is the probability of exceedance in 50 years, and here you have the different values of tsunami elevation. And these are the graphs which I obtained from a very important park there in Long Beach, which is called the Aqua Park. Okay, and you can see that effects are important. And here actually we have some solution for San Francisco and Morro Bay. Okay. My assumption. Cannot put the sound. Okay, so the tide, when I'm including the tide in my model, I'm saying that we are having a fixed sea level moving up and down. Do you know what is that? What do you think is that? A river. Actually, we saw it in coastal engineering this one or not? I don't know. What do you think is that? Is a river? It looks like a river. Yeah. Okay. This is not a river. It's actually a channel, a tidal channel or an oceanic channel. This is a channel which is called Chacao, Canal Chacao in southern Chile. And this channel connects an inland sea, a huge inland sea, with the rest of the Pacific Ocean. And this is a place in Chile which has the largest flow currents created by tides, one of the largest in the world.
Why is it?
Hawaii, we are talking about 40. Now, why we are talking that in the place with maximum current, we are talking about 1.5 kilometers, 1.2 kilometers. And in terms of land, it's like 40 kilometers, more or less. Okay, this place, I have devoted many years on this channel. I did my undergraduate study because I wanted to understand the tidal energy potential of this area. And also I did the design of the tsunami tide design of a suspended bridge in this region, which is under construction, the longest one in South America. The point of this video is that actually tides come with currents sometimes. So it's not only the sea level. So that means that we need to build a model which actually can simulate the interaction of tidal currents, for example, for these areas, with the currents of the tsunami. That is something that our models that we have right now are not doing. And this is what we are building right now in the lab. A tsunami model which can couple with tidal currents and can make a tsunami hazard assessment in sites like this one. And try to understand the nonlinear interaction between both. Okay, just quickly, how many minutes I have? 10 minutes. Okay, let's go fast. Another model, which is pretty interesting, that I started working 2 years ago, or 2 years I started in January 2022, is related with volcanic tsunami. So This image, this satellite image is the Tonga volcano that made eruption in January 15 at 4:20 a.m. of January 15. That volcano was pretty spectacular because it created a huge explosion. Why? Because the volcano was under the water, but also was sufficiently shallow to create an explosive eruption in that area. That explosion created an acoustic wave that travels all around the world, and even more, it created a big tsunami that actually crosses continents. This volcanic eruption even created a tsunami in the Atlantic Ocean. When I hear that thing for the first time, I thought that the scientist was crazy, but he was right. Okay, so assume that day I woke up at 7 a.m. and I received the emergency advisory from the Pacific Tsunami Warning System in my cell phone saying that we need to be careful because a tsunami is coming. And this was 7 a.m. Saturday. I was sleeping and sleeping more than a week. Of course, you want to take rest on Saturday. And a friend called me and I said, don't worry, it was just a volcanic eruption. 9 a.m., we started to see the picture of everything getting flooded because of the tsunami. And I was saying, oh my God, again, I was wrong. So, everybody remember this tsunami that happened January 2022? Maybe not. That's normal that people forget. Some people may remind that there was a very important flooding of Santa Cruz Bay. There was some marinas which were get flooded. Here is San Diego Marina was destroyed. Some docking sites were destroyed, etc. Anyway, it was some economic losses, which we are talking about hundreds of thousands of dollars of losses because of that. Okay, a chronology, January 16. A very important professor in Rhode Island University started to send emails saying that he was impressed by the fast arrival times of the tsunami in some locations. Typically, a tsunami has a certain velocity in which they propagate in the ocean, but these tsunamis were arriving earlier than that. And that was weird. The first thought from my side was, okay, there was a problem with the instrument. There was an error with the instrument. But then we started to see that it was pretty obvious that tsunamis were arriving earlier than expected. So we started to analyze the next day the dark buoys. We downloaded all the dark buoys with Matias Carvajal, a friend from Chile, and also I was working with Duncan Agnew, a geophysicist from here from Scripps. And we started to see the biggest arrival times, the biggest waves were arriving with the typical arrival time we know from waves propagating over the ocean. But anyway, we were starting to see some noise even before that big waves. Okay, so that was kind of weird. In January 20, we learned that the tsunami in Tonga was big, but not so big. So then that was opposite to our understanding, because in order to have big waves in the US, certainly at the source, the tsunami had to be huge. And we didn't have that. In January 20, we learned that in Tonga, next to the volcano, the tsunami was big, but not too big. So certainly something weird was happening here. And then at 6:36 a.m. of January 20, we started to analyze the records of the tsunami in the Atlantic, and we started to observe tsunamis in the Atlantic. So basically the tsunami was crossing the Americas and it was arriving to the Atlantic Ocean. This volcano is located in the Pacific. So basically the tsunami was crossing a continent. How was that possible? So then we started to think, oh my God, maybe the tsunami were generated from the atmosphere. We started to think about that. So finally, February 4th, Facilitito, who is a scientist from the NOAA, he shared a preliminary model and showed that actually the atmosphere was forcing the ocean and was creating the tsunami in the Atlantic. out of this planet, out of my mind. So basically, after I hear that, I say, okay, I have to spend my time developing a model for this thing because it's pretty awesome. Okay, so what we did with Matías Carvajal, we wrote a paper which was published a couple of weeks after the event, and we started to see that actually the biggest way we're arriving with a certain arrival time in the Pacific Ocean, which was in agreement with a wave propagating over the water. But then these little points that you can see here are actually showing waves that are arriving before that arrival. So certainly waves were generated and traveling with the atmosphere, which can travel, a wave in the atmosphere can travel faster than a wave, a shallow wave in the water. So then, of course, Luca and Agnew started to tell us, okay, we need to take a look about what happened in Krakatoa in 1883. Krakatoa basically created a tsunami in an event which was super similar to the one that happened in Tonga in 2022. So basically, these two events were very similar in all what it happened there. So what we start to see was to review papers from 1886. And we started to see that people actually saw tsunamis at the other continent. So actually that was true, and that happened in the past. So we started to try to analyze the effect. And basically here in this diagram that you can see here, let me put play here, you can see in this video an atmospheric wave, and you can see how that atmospheric wave is actually creating tsunamis in the ocean, which is represented by the, oh, sorry. Let me put it again. So you will have the classic tsunami, but in addition to the classic tsunami, you will have an atmospheric wave which actually travels very fast. And that atmospheric wave is creating two types of waves, a decoupled a meteorological tsunami or a decoupled a pressure tsunami and a coupled tsunami, which is traveling with the atmospheric wave. Okay? So certainly the atmospheric perturbation or an atmospheric wave can create tsunami, and we can see it with our mind. But something we discovered, and this was the reason of the second paper we wrote, like we finally published a month ago. Actually, we submitted to Nature this paper in January, but they rejected. I don't know why. You remember I was showing to you these videos in January? Okay, one of the things we discovered is actually that pressure wave traveling in the atmosphere is affected by winds. And now we have a problem in which tsunamis depends on the winds that you have in the atmosphere. And how is that? Actually, in this video, the yellow one shows the intensity of the wind. And here you can see a wave in segmental line, which is not affected by wind. And then you have the continuous line of the same wave, but affected by wind. What happens if the wind is traveling against you? What will happen with the wave? The wave will start to travel slower. And that was a discovery with this in January of last year. And you can see that the changes are significant. We were not the creator of the idea. Actually, a scientist in 1884, after the Krakatoa tsunami, he said that he was thinking that winds were modifying the air wave and also was modifying the tsunami wave. But he didn't have any model or any formula to prove it. 140 years ago, we finally had the tools to show that he was right. Okay, as an example, and here we will move quickly, the figure at the top is showing to you the pressure wave traveling in the air, taken from satellites. The middle panel is showing my model considering winds. And this model is a model which everybody was using before this paper, in which you were not having winds. Can you see the effect of the wind? Do you want to see it again? Compare the satellite with the two models and tell me which one is better. Here, they are more or less the same, but look at what happened now. You can see how the new model is capturing more physics. Okay, this has a huge implications because the intensity of the atmospheric wave will be different, the arrival times will be different, and therefore the tsunamis that you will create with that atmospheric wave will be different. And therefore the tsunami is affected by the wind indirectly. You see? Have you ever thought, I never would even imagine that the wind can change the way that tsunami propagates. It's crazy. Okay, here are basically some additional models in which I'm showing basically the match with atmospheric pressure records, and here's some measurements of the tsunami wave in some buoys which recorded. And you can see that actually the match is pretty awesome. Okay, we are still working because still we need to improve the quality of the accuracy of the model, basically trying to refine topography and wind. But certainly we are in good track. Okay, I will jump this thing because we are running out of time, but just a conclusion about this volcanic tsunami model, I can tell you that this would be impossible if you don't have data. Records were very important. If I wouldn't have the satellite imagery, I would never thought that the wind was actually playing a role modifying this pressure, tsunamigenic pressure waves traveling in the air. Okay? And the second great knowledge that was basically suggested by 1883 is basically that the role of this acoustic wave, the atmospheric wave, is very important causing tsunamis, especially in the Atlantic Ocean. It's the only way you can have a tsunami in the Atlantic Ocean due to volcanic eruptions in the Pacific. And finally, we are still investigating what are the most relevant variables, because at the end of the day, we want this model to work in an early warning system. So we can use it for the next eruption which generates tsunamis. Okay? So after you have everything, this is just a demo of the things we are doing in the lab. After you can understand the tsunami hazard, you can go and start to study the cascading effects. Basically, for example, if you have currents, what happens with the spills of contaminants in the ocean? And actually that video is showing an advection diffusion model, which is coupled with actually not a tsunami model, but with a tidal model. This is the checkout channel, the one that I showed you in the video. Okay? So you can see how if you spill contaminants on that channel, how they spread over the channel. And you see that the tide goes forward and backward because the tide has a cycle, right? So it will move to one side, then to the other. It's a tidal wave. Another things that we are trying to do in the lab is basically try to understand inundation. Actually, this is the natural gas port that I was telling you, and that is a study in which we were studying the inundation of the facility. That is a seawater intake system of a port. And we are observing how it's getting flooded. And in order to avoid this problem, the client, the port, asked us to design a breakwater. These are the type of breakwater we are doing in coastal engineering. But this is for a tsunami, which is, actually this is a, you can compare the size of the thing, it's from another planet. Okay, so that's all I can show you. Okay, we're still doing a lot of different things related not only with tsunamis, but also with coastal hazards. We are looking for more people if interested. We have a lab, we have capacity, we only need more hands to develop more ideas. So that's all, and I hope you like it, and question if you have. What time it is, by the way? We still have time. Thank you very much.
So when we were talking about it, I was just thinking about like weather models, which is like highly nonlinear. So I assume the tsunamis are like also highly nonlinear. So like, for example, the cascading effect with the contaminants, like how faithful is that, especially over time?
Yeah, when we study tsunamis, one of the things that we need to consider is the nonlinearity of the tsunami wave when you are in shallow waters. In the middle of the ocean, for example, in the generation zone, non-linearity is not important. So you can work with a linear model. However, when you start to get closer to the shallow area and your amplitude start to become comparable to your water depths, then non-linearity becomes important. Now, another important thing that we can consider with other type of model, not with this one, because the ones that I'm using are only long wave equations or shallow water wave equations. Another problem that you have is that sometimes the tsunami waves or some waves are sufficiently short that your dispersion starts to become important, the frequency dispersion. The people who did coastal, Regan, or the this know what is the dispersion. So dispersion means that waves with different wavelength will move at different phase speed. And basically you will start to spread your energy. Not a spread, because that would be diffusion, but you will start to split the energy into different ways. When you have a dispersion, basically you will change the shape of your wave and you will change the hydrodynamic next to the coast. And for that, you will need to consider other type of model. For example, a Business wave model. The problem with the Business wave model is that it will take forever to run in a boat, while the nonlinear shallow water equation run in half an hour for those events that you saw. So it's all about what is important. You want to try to keep as simple as possible, but at some point you cannot deal with that simple model and you will need to change to something more complicated. For the volcanic tsunami, for example, now I'm having a meeting with other people in Japan, who is trying to understand better the 3D structure of the atmosphere in order to do the volcanic tsunami. And they have been working with the structure in 3D and trying to see how we can get a two-dimensional average, which is the one I'm using in my model, in order to improve the accuracy of that volcanic tsunami. And those are things that we are doing right now. What is the answer? We still don't know. Of course, the people who have the most sophisticated model will tell you, no, let's do the most sophisticated model, but sometimes you need to have something that you can run in your laptop, not in a supercomputer. So then there are trade-offs that you need to check, and for that is because we have research. See? But nonlinearity is one of the important. This one has nonlinearity, so your question, you are fine, but the dispersion then is something that I'm worried about, that we need to evaluate. You see? Yep, correct.
Might be a stupid question, but so
No,
a tsunami triggered by an earthquake, right? You have at least in some sense 3 different waves. You have the wave that's propagating through the solid mantle, you have the wave in the water, and then you have the atmospheric or wind effect, right?
And everything is coupled, by the way.
Right, and so can you tell a little bit about, they're all in some ways different speeds. Which one is the fastest?
So when you, this is related with earthquake, not even with volcanic, but let's talk about that. When you have the earthquake, you have a family of type of wave that you generate, which typically have different wavelengths and propagated in different mediums. The one that propagate in the solid earth are the typical P wave, S wave, and the surface wave, seismic waves. Okay, those travel super fast. In addition to that, you have the waves that propagate in the water, and the classic one is the tsunami wave, the long wave. However, you also create other type of waves. Okay. You have acoustic waves, which actually travel much faster, travel at the velocity of the speed of sound in the water. And actually, some people in MIT and in what is the name of this guy in the UK? Well, there is a group of people who are working with acoustic wave traveling in the ocean, because they are thinking that if they can read the acoustic wave traveling in the ocean, they can know before the tsunami arrives that a tsunami is coming, because you can relate this type of wave with the tsunami wave. And then you have atmospheric waves. And actually, when we were discussing the problem of the volcanic tsunami, then the question arises that actually maybe even the earthquake are creating pressure disturbances. And that is true, that happened. For an earthquake, in order to create a wave, an atmospheric wave that can create tsunamis, probably we haven't seen that and probably those are very weak, but certainly you can create some perturbation. For example, some people are working with the ionosphere perturbation after an earthquake because those travel fast. And for example, if you have a GPS antenna, you can understand what is the perturbance in the ionosphere because your GPS signal are coming from satellites. So basically in the path, you will create a perturbation. And some people are thinking that you can create an early warning system using that information from that kind of way. So at the end of the day, when you have an earthquake, you have, you don't imagine how many type of waves traveling in different media and from different frequencies.
So in the model, then which ones do you
Ah.
definitely consider and which ones do you not, right?
Okay, for the tsunami wave from an earthquake, typically you are working with the lowest frequency. So you even forget about the seismic wave. And actually for a tsunami, you just work with the deformation. When we started to work with the volcanic tsunami, then we started to be in trouble because you wanted to neglect the waves, but now you have this new wave, which is a huge acoustic wave traveling in the air, and now you cannot neglect that. And then you need to understand the physics of that. Luckily, the dominant wave traveling in the atmosphere still can be treated as a non-dispersive wave. But then now people are thinking that maybe we should improve that model and try to include more dispersion and try to get other modes of the acoustic gravity wave, which is things that people are doing.
Do you think it will matter adding?
People in Japan think that one of the signals they saw are probably other modes of the acoustic gravity wave, which are traveling slower, and because they are traveling slower, they have more capacity to create tsunami. That is the hypothesis of the Japanese people, actually. They are working a lot with that. Yeah, but not in the Atlantic, because based on the satellite, you can see that there are no other modes, important modes. But maybe in the Pacific, they are still significant.
How come winds don't affect the earthquake tsunami speed, because they do with the volcanic? How come winds don't affect the earthquake tsunami speeds? Because you said they travel.
Because the shear stress that you can create by a wind in a tsunami wave that propagates in the water probably is negligible, that force. But in this volcanic tsunami, the problem is that your tsunamigenic source, which is the pressure wave, that is the one affected by the wind.
Is the volcanic one smaller?
It typically is smaller, yeah. But actually, it's not a matter of amplitude. It's more a matter of what you are perturbing. In the case of the volcanic tsunami, the far-field volcanic tsunami, is because your pressure wave is traveling in the air. And then the air is the domain of the wind, basically. It's the circulation of the planet.
Caused the wind? Tsunami caused the wind, so.
That is a good question. I don't know, you say the opposite, like if you have a tsunami, you will create a wind? Maybe. I don't have the answer. I don't know if you can do a scaling analysis, right? Then you need to deal with the shear stress there, so I don't know. That is a good question. There is.
You mentioned designing a suspended bridge in Chile across that channel that had the crazy current.
Mm-hmm.
Would they drive tiles into that? Because I can't imagine not having a scour to protect your bridge.
That bridge is possible because in the middle of that 1 kilometer width that you were asking, Jose, there is a cement in the middle. And basically the pile, the central pylon is basically anchored to that cement. And they spent like 3 years putting the piloting in order to anchor that pylon. So it was, and actually they did a lot of study about the stability of the rock in that cement, because you can perforate it in order to build that pylon. Yeah, it's the only reason why you can build a suspended bridge there.
Yeah.
Okay.
Yes, Lieutenant Rico, one more question.
Thank you, guys, for the question.